Okay, very quickly, a short lesson on polynomials. I did half of this in period 3, a tiny bit of it in period 8, and none of it in period 4. Here is a polynomial, 6x cubed plus 7x squared minus 14x minus 8. And we can search for roots. How? Well, one thing we can do is to use Descartes' rule of signs. We look at f of negative x and we get negative 6x cubed plus 7x squared plus 14x minus 8. There's one sign change in f from negative to positive, and from negative to positive to negative there are two sign changes in negative x. And so the chart looks like this. We learn that there's guaranteed to be one positive real root, but there might be two negative real roots, or there might be none. So that wasn't super helpful. We can also apply the rational root theorem. What are the possible rational roots for this polynomial? Well, the denominator has to be a factor of the leading coefficient. So 1, 2, 3, 6, and the numerator has to be a factor of the constant term. So 1, 2, 4, 8. So there's actually kind of a lot of them. That's sort of annoying. Okay, let's just try some numbers and see what happens. The first thing I did is to try x equals 1 to see if that's a guess. Okay, well, I'm going to try 1 as a root, and I get 6. And I think what happens is it doesn't work. So that makes me sad. And let's see. I will try something else. How about I try 2? Let's see if that works. And I think that also doesn't work. So now I'm really sad. And that's what we have. Okay, well, even though 1 didn't work and 2 didn't work, something happened when I tried 2, which is that I got a positive remainder, which is 40, and also all of the coefficients of my quotient were positive, which is to say that the entire bottom row of the synthetic division consisted of all positive numbers. So I feel like that means something because, well, it means that this quotient is going to just keep getting bigger and bigger. And if my remainder is positive, and my quotient polynomial just keeps growing and growing, then my function is just going to grow and grow. To be more careful about this, what really happened here when I tried to see if 2 was a root was I divided through by x minus 2. And when I divided through by x minus 2, I got 6x squared plus 19x plus 24 with a remainder of 40. Which means that this polynomial can be represented as x minus 2 times 6x squared plus 19x plus 24 plus 40. And writing the polynomial in this form reveals that there cannot be any roots in this polynomial beyond 2. And that's because if I take a number that's bigger than 2, well then x minus 2 is positive. And if I plug that positive number into this quotient, then I'm also going to get something positive, because if x is bigger than 2, then 6x squared is positive, and 19x is going to be positive, and of course 24 is positive. It's also true that the remainder, 40, is positive. And so my divisor is positive, and my quotient is positive, so I'm multiplying two positive numbers, and I'm adding positive remainder. It means that this whole thing is positive. In other words, phrased slightly differently, if x is bigger than 2, then my function is guaranteed to be positive. Which means, in picture form, that if I start over here at 2, if I start over here at 2, my function currently has value 40, and it's just going to go up and up and up from there. Therefore, if this, based on this analysis, there cannot be any roots bigger than 2. So f has no roots beyond x equals 2. This is known as the upper bound theorem. Okay, and I ran out of space to say any more, so I'll just say it in words. The upper bound theorem says that if you have a polynomial, and you plug a positive number into that polynomial, and you get back all positive numbers in the synthetic division step, which is really another way of saying that your remainder is positive and your quotient is positive, then beyond that number that you tried, my function is always positive and there can be no roots. So anytime this happens, don't look for any roots bigger than 2, because there can't possibly be any. Alright, and that's what I did in period 3 and sort of in period 8, but the thing I didn't do in any class was the variant, and the variant happens with negative numbers. There's a different rule for negative numbers, and it's a little bit more subtle. So suppose we try x equals -4 to see if that's a root. Well, here again we have 6, 7, -14, -8, and if I drop this down, okay, -24, -17, 68, 54, that's right, yeah, and some big number, -216, so it's -224. Okay, so certainly -4 is not a root, and so I'm sad. Can I learn anything from this? Yes, I can. Because these numbers alternate, a similar analysis will reveal something about this function. After all, if I tried -4, what I really just did is divided the polynomial through by x plus 4. And so it means this polynomial can be written as x plus 4 times 6x squared minus 17x plus 54, and then with the remainder of 224. Okay, here it's less obvious what's going on, but if I try a number which is less than -4, then I can say that x plus 4, the divisor, is negative. Plug in -5, say. Well, what can I say about this quotient? Because these signs alternate, and that's the key to this theorem, the positive, negative, positive, negative, it means that if I plug in -4 into this quadratic term, I'm going to get a positive thing. And if I plug a -4 into this linear term, I get negative times negative, so that's also positive, and then 54 is positive. And finally, I have a negative remainder. In other words, if x is a negative number and the signs in the quotient polynomial are alternating, then this polynomial is positive. This quotient is positive. But if my divisor is negative and my quotient is positive, then I'm multiplying a negative by a positive. My remainder is negative. It means the divisor times the quotient will be negative, and added to a negative remainder will give me something negative. So, if x is less than -4, my function is guaranteed to be negative. And thus there cannot be any roots less than -4. The picture kind of goes something like this. Here's -4. I'm way down here at -224. And this function to the left of -4 is just going down, down, down. So, f has no roots beyond -4, where by beyond I mean to the left of -4. And this is known as the lower bound theorem, and the lower bound theorem says if you plug a negative number into a polynomial and the signs alternate, then by performing this analysis we can see that there can be no roots less than that negative number that you tried. Therefore, if this should ever happen while guessing roots, know that there can be no roots less than -4, and so we shouldn't look there. Okay, so blind guessing the rational root theorem, the intermediate value theorem, Descartes' rule of signs, and these upper bound and lower bound theorems can be combined together to make the search for roots a lot easier. Okay, thanks. Bye.